So now here is what we referred to already in the previous unit when we were talking about the Lebesgue integral. It is, well, it's not the chain rule. The chain rule is for derivatives, but it's the version of chain rules. So in the first part of this video lecture, we have discussed how can we define a measure from another measure through a density. We saw an example where from the Lebesgue measure on the real line, we define a probability measure. Then we we give a name to this function. It's called Radon-Nikodym derivative, and discuss the two different situations where this can happen. We can either define a new measure using a function, or we can have two measures and wonder whether they are related by a function. Then we saw a concrete example again of how from one measure we define another measure by changing the weights through some specification of a density. And now we're going to see the analogous to what in calculus is the substitution rule or change of variable, which is the dual of what is the chain rule for derivative. And we already mentioned it back in the previous unit, this change of variable, but we didn't quite make sense of what that was. What this change of variable, this push forward of a measure. We just mentioned that in practice, we can write explicitly one measure as a multiple of another measure through some density, we would be able to do this calculation. Now here it is. Okay. So if we have a Radon-Nikodym derivative, okay, so this is the assumption of this proposition. So we have two measures, mu and nu, such that the density of nu with respect to mu exists. Okay. And now we want to integrate a non-negative extended Borel function. Why non-negative? Does it have to be non-negative? No, it does not have to be non-negative, but the theory is much simpler if everything is presented for non-negative functions, because it's very easy to say whether a function is non-negative. And later on, when you want to apply it to another function, well, you just split into the positive part and negative part. But it's much better to do it on the fly, on a case-by-case basis, than try to state precisely all the corner cases of, well, what happens when G is not non-negative. So let us stick to this simple presentation, which is the non-negative measure theory here. So let's come back. When G is a non-negative extended Borel function, so we can either integrate G with respect to the new measure nu, so this is the measure nu, such that mu has a density with respect to mu, or we can replace and integrate with respect to the original measure mu if we multiply G by the density. And now here, of course, so you see I can do this silly movement here. This is, of course, not something you can do in practice. Well, or maybe that's not something you can do in theory, but it works. Even though this is a measure, that this is the indication that we are integrating with respect to the measure mu, and this is a function. So just the fact that there is a notation here with a differential showing that we are using mu to compute the integral, and we use also notation of differential to say we're talking about the density of a function with respect to another. The fact that these two are canceled like this is just that shows that the notation has been chosen wisely. Okay. Now let's see why this proposition is true. Here's a proof, and now we are reproducing the pattern from the previous unit. We start with a function that only takes two values, 0 or 1. So this is always an indicator function, and let's say this is an indicator function of a measurable set. Okay? And then what we have here is we want to compute the integral of on omega of the indicator of a certain set with respect to the new measure nu. And this is nu of A because the integral is unitary. Okay? So this is an axiom of an integral, not really an axiom because we proved it later on, but this is an axiom that the integral of an indicator function is the measure of that set. And now we're computing the measure of a set. So this is true because this is a definition of density. Density is the function that we can plug here, and that will make this computation give the same result for every set A. So this is true by the definition of density, this equality here. And now here, what is this? This is just the definition of what it means to integrate on a set, a subset A. And now if we forget all the intermediate steps, what did we get here? What we get is the statement of the proposition. Let me go back. The statement of the proposition, this integral equal to this integral, and we have just shown this is true when the function g is the indicator of some set. But now, as usual, following the pattern that we have followed already quite a few times in the previous unit, since the integral is linear, and so meaning adding two functions here and here will give us the result to add up, and multiplying by constants also. So by linearity, this property, what property? This property here, it will hold when g is any non-negative simple function. Well, we don't really need it to be non-negative, but that's enough, because now we can take by monotone convergence theorem, and by the fact that functions can always be approximated from below by non-negative simple functions, then we can take a limit on both sides, and this will hold for every function g. And this concludes the proof of the proposition, and this concludes this video lecture.